Welcome to Everyday Mathematics. Today we look at a problem that featured in the movie The Man Who Knew Infinity. And that is based on the life of this Indian mathematician known as Srinivasa Ramanujan. So this is an interesting movie. And one of the problems that featured in that movie was this problem. The definite integral from from theta equals to 0 to theta equals to pi over 2 of 1 over square root of 1 minus k squared sine squared theta. And we see in that movie this guy, the actor, just going straight and answering or writing down the answer of this integral without really showing his working, and the professor is really intrigued and surprised. So this also is featured in this book, Almost Impossible Integral Sums and Series, and it's problem number 43. So for those of you who are interested. So without much ado, we'll go ahead and solve this problem. But before I move forward to do that, quick encouragement to those who haven't subscribed to our channel to please consider subscribing to our channel. For those who may like what we're doing here, please consider leaving a like. And if you think this might actually help somebody, please do share with them. So let's move forward and solve this problem. In order to solve this problem, there's one integral that is of interest. So we'll solve this integral from x equals to 0 to x equals to pi over 2 of 1 over minus a sine squared of x. So we'll use the identity sine squared x plus cosine squared x is equals to 1. Let's use this identity. And then we'll use to substitute for that. So this problem will be equal to the integral shown here. And then what do we get next? We can bring this and this together. So we have 0 to pi over 2, 1 over 1 minus a sine squared x plus cosine squared x. And we can divide the numerator and the denominator with cosine squared x, and that leads us to 1 over cosine squared x over 1 minus a tan squared x plus 1 dx. So what is 1 over cosine squared x? 1 over cosine squared x is the same as x squared x, and so our problem now becomes 0 to pi over 2 sec squared x over 1 minus a tan squared x plus 1. So we can substitute for this interesting part, and we'll say let u be equal to the square root of 1 minus a tan of x, such that du dx is equals to square root of 1 minus a sec squared x. And so what that means is that du over the square root of 1 minus a is equals to sec squared dx. So we can use that to substitute for whatever is in the numerator. Now, when x equals to 0, what does that mean? U tends to tan of 0, which equals to 0 when x equals to pi over 2 that means that u tends to infinity. Okay, because when x tends to pi over 2, it means that tangent of x tends to infinity, and so square root of 1 minus a times that will be that. Anyway, so what do we do next? What we do next is we have our problem that is this. So this in the u domain, we're going to have 0, infinity, and then this part here becomes du over square root of 1 minus a over u squared plus 1, which is equals to 1 over square root of 1 minus a 0 pi du. That is 1 over u squared. So this is equals to 1 over arctangent of u 0 infinity, which is now 1 over as u tends to infinity, arctangent of u minus limit as u tends to 0, arctangent of u. This tends to 0, and this tends to pi over 2. And so our problem from x equals to 0 to x equals to pi over 2 of 1 over a sine squared of x is equals to pi over 2 times 1 over 1 minus a. This is a very important link for us to solve our problem, and our problem is the integral from theta equals to 0 to theta equals to pi over 2 of 1 over the square root of 1 minus k squared sine squared theta. So this is our problem. What is this equal to? And that is, we are going to focus on that, and there are a couple of things that we're going to have to invoke, and that is the Wallace integral, going forward. So in the next slide, we'll see how to solve this problem. So this is our problem, right? Integral from theta equals to 0 to theta equals to pi over 2 of 1 over the square root of 1 minus k squared sine squared theta. So the important part for us is to see that obviously from what we had shown previously, that the integral from 0 to pi over 2 of 1 over a sine squared of x we showed that, and so if a is equal to k squared sine squared theta, if a is equals to that, then it means that 1 over the square root of 1 minus k squared sine squared theta is equal to 2 over pi, the integral from 0 to pi over 2 of, instead of x, let's use phi over minus k squared sine squared theta times sine squared phi. So using that, we're going to now substitute that into our integrand. So our problem now becomes, in place of, there's a hidden one, in place of this, we have integral from 0 to pi over 2 in bracket 2 over pi 0 to pi over 2 d phi over 1 minus k squared sine squared phi sine squared theta, close bracket, that. And we can pull out this constant, so we have 2 pi over 0 pi over 2 1 over 1 minus k squared sine square phi sine square theta d phi d theta. So that's what our problem has become now, and we're going to try to now simplify that further and come to an interesting problem. So our problem has come to this point where we have we have 1 over 1 minus k squared sine squared phi sine squared theta So we're going to use an expression so if we have so this here is a geometric progression to infinity. And so let's use that to now re-express our problem too. K, small k, 2n sine to the power 2n of phi sine to the 2n of theta d phi rather d theta. So we can rearrange things to help us get some So we can bring the summation sign out, because the integral of the summation of items is the same as the sum of integral of the independent items. So 0 to pi over 2. You can even bring k out there because it's a constant. 0 pi over 2 sine 2n pi sine so since phi and theta are independent from one another, we can actually separate these into two separate, the product of two separate integrals. Zero. So these two separate integrals, they're very similar to one another. We didn't just say it's a square of the two integrals, but this is what we call the Wallis integral. Right? So what we're going to do is we're going to take a small detour and see how this integral can be solved. Then we come back to the solution to this integral and plug in what values the Wallis integral gives us. So let's take that detour and solve for the Wallis integral first. Let's go and try to solve what we call the Wallis integral, right? So if you have our integral Wn such that it's the integral from x equals to 0 to pi over 2 of sine to the n of x, this is the same as integral where we can divide it so that it's to the n of minus 2 times, okay, and we know that sine squared x is the same as 1 minus cosine square of x. Is the same as those two integrals. Okay. So what do we do? Let's focus on this integral here and see what that leads us to. So solving for same as, I can re-express this as the integral from x equals to 0 to x equals pi over 2 of the derivative of sine to the minus 1 over n minus 1 times cosine of x. And then using integration by parts, where if we have a product of capital V function times the derivative of function u, when you integrate that, you get u v minus v, rather u dv, right? So using this, we can consider these to be u and this to be v, so that our integral becomes 1 over n minus 1 sine of to the n minus 1 x cosine of x, that's uv, 0 pi over 2 minus 0 to pi over 2, 1 over n minus 1 sine of to the n minus 1 x times the derivative of cosine of x. This is dv, right? And then, so this becomes 1 2 cosine pi over 2 minus 1 over n minus 1 sine to the n minus 1 of 0 cosine of 0. See, this goes to 0 because cosine pi over 2 is 0. This goes to 0 because sine of 0 is 0. Minus 0 to pi over 2, 1 over n minus 1 sine of n minus 1 times negative sine of x. This minus and this minus interact, so we eventually have 1 over n minus 1 double from 0 to pi over 2 sine to the n. Okay, so what do we see here? We see that our previous integral, which was the integral from 0 to pi over 2 or sine to the n of x, was equal to the integral from 0 to pi over 2 of sine to the n minus 2 of x minus 0 to pi over 2 of the n minus 2 of x cosine squared of x. And we found that this is the same as 1 over n minus 1, 0 pi over 2 sine to the n of x. So if this be Wn, this is the same as Wn minus 2 minus 1 over n Wn. Bring this here by adding both sides. So we have 1 plus 1 over n minus 1 W of n is equals to Wn minus 2. And this becomes n over n minus 1 Wn is equals to Wn minus 2, meaning that Wn is the same as n minus 1 over n Wn minus 2. This is very, very important. This is very, very important. So we have shown that W of n is equal to n over 1 over n of W of n minus 2. And this could also be equal to n of, so we see n minus 2 coming at the top there, and n minus 3 at the top of W of n minus 4, and so on and so on and so on. So effectively what this tells us is that if we had something like that, which is even, we'll have 2n minus 1 over 2n minus 3 over 2n minus 2 all the way up to 1 over 2 W of 0. Okay, and well, this is, what about W of 2n plus 1, which is odd? This is even, this is odd. So we'll have 2n over 2n plus 1 Then we have 2n minus 2 over 2n minus 1, all the way up to 2 3 and w of 1. That is that. And so what is w of 0? W of 0 is 0 to pi over 2. Sine to the power 0 is going to be 1, so that's that. So this is pi over 2. And what is that? That is 0 pi over 2 sine of x, which is equals to negative cosine of x, which is 1. So that is what we have. Now let's try to express this in a more compact form. So we've shown that the Wallis integral to the 2n is the same as you say 2n minus 1 over 2n minus 3 over 2n minus 2 all the way up to 1 over 2 w0, which is pi over 2, and w2n plus 1 is the same as 2n over 2n plus 1, 2n minus 2 over 2n minus 1, all the way up to 2 over 3 times 1. Now this is interesting because we see 2n minus 1 skipping 2, so double factorial over 2n double factorial times pi over 2 is the same as 2n double factorial over 2n plus 1 double factorial times 1. Okay, so we are really interested in this guy here, right, for our problem. So since this is equals to over 2n times pi over 2, what this equals to is we could simplify it a little bit more, because we could pull the 2 out here, n, but we could actually do that, and then we have n factorial squared, so that we do have 2n factorial times pi over 2. And that is because what we've done here is we have done that 2n, and we've plugged a 2n, and we've plugged a 2n minus 2 all the way down to 1, and that means we have 2n squared, we have 2n minus 2 squared, 2 squared, and so when we pull that the 2 out, we have 2 to the n times 2 to the n, which is 2, so this becomes that, and we have n factorial squared, and at the top we just have 2n factorial, right? So we've just padded these guys in and compensated in the denominator so that we have 1, and so that is what has led us to this. Okay, so with that in mind, we have shown that our Wallace integral to the 0 to pi over 2 sine to the power 2n of x dx is equal to 2n factorial over 2 to the power 2n bracket n factorial squared times pi over 2. So our previous problem, which we were trying to solve, is as follows. We were trying to solve, because our problem had gotten us to that, summation from n is equals to 0 to infinity of k to the 2n 0 pi over 2 sine to the 2 of n of theta 0 pi over 2 sine the 2 of n of I. And so this and that would take whatever we have there. So we have to n to n to n okay, and let's see how we can expand that, right? So we said our problem has gotten us to this point of k to the 2n of brackets 2n factorial over 2 to the 2n over n squared pi over 2, and the same thing repeats over 2. Bring these constants out, so we have 2 pi over 2 pi over 2, and we see this cancel, 0. N squared, so this becomes pi over 2 to the 2n in bracket 2n factorial over 2 to the 2n over, so which becomes pi over 2 in brackets 1 plus when n equals to 0, that just becomes 1 because 0 factorial is 1. We don't want to go into the details of that. That might be another video. But then we have, when k equals to 1, we have 2 factorial up here. We have 2 to the power 2. We have 1 factorial squared, which is just 1. squared plus k to the power of 4 when n equals to 2. And we have 4 factorial up here, and then we have 2 to the power of 4, and here we have 2 factorial squared, and so on and so on and so on. Okay, which is equals to pi over 2 1 plus 1 over 2 squared k squared plus 3 2 1, and here we have 4 times 4 times, and then we have the square of 2 there. So cancel that, and then 1 2 for the square goes away, but we're left with 1. So eventually what we and sorry, there's k to the 4 there without forgetting, and so on and so on. So we come to pi over 2 1 plus 1 over 2 squared k squared plus 3 times 1 over 4 times 2 k to the 4, and so on. So in other words, our integral from 0 to pi over 2 of 1, the square root of 1 minus k squared sine squared theta, and this is the integral that featured in that video. We're going to watch that video in a short while. Is what is shown here. There's a square there, sorry. 2 k to the 4, and it's interesting because when k is equals to 1, that means that we have 0 to pi over 2 over the square root of 1 minus sine square theta, which is the same as pi over 2 1 plus a half squared plus 3 1 over 4 2 squared. Sorry, there's a square there. There's a square there. K to the 4 all the way, and when k is equals to I, we get 0 pi over 2 1 over square root of 1 plus sine square theta equals to pi over 2, and in that scenario we have 1 minus a half squared plus 3 1 over 4 times 2 squared k to the 4, and to the 6 it will be a minus, and so on and so on and so on. So that kind of brings us to the end of our video today. We won't want to dwell so much on the other things that we can exploit from this problem, but it's a powerful, very powerful integral. We could even substitute for when we say x equals to sine theta, and then see how the problem evolves and so on. So without much ado, I'm glad you've hung around with us, and if you like the video, please don't hesitate to leave a like. If you haven't subscribed, we encourage you to subscribe. Here at Everyday Mathematics, what we do is we do enjoy solving these problems. I will leave a short video showing how this problem featured in that movie, The Man Who Knew Infinity, or The Man Who Knew Infinity, in Srinivasa Ramanujan. So until next time, have a fantastic, fantastic day ahead. Bye-bye.
All right. Now, are you following this?
Yes, sir. Most excitedly.
Well, you don't appear to be taking any notes. Is there something you'd like to contribute? You need the chalk.
But I hadn't completed that proof. How do you know? I don't know. I just do.